Hello and welcome to a last video in this chapter, namely to a video on the horizontal Jeffcott rotor and journal bearings. So what is the difference between the Jeffcott rotor and a rigid rotor? Well, it's the shaft stiffness C. So we introduce here a new parameter, the shaft stiffness, and we would like to see and to highlight the influence of that shaft stiffness on the self-excited and the externally excited, so by an imbalance excited, vibrations, oscillations of that rotordynamic system. So first of all, let me show to you the equations of motion. So the equations of motion have to be modified. You can compare this to the classical Jeffcott rotor, but in elastic bearings. So we have two sets of equation. The first set of equation is the set of equation we also obtained for the rigid rotor, composed by the inertial forces, gravity, and the imbalance excitation. Once again, if you look at that equation, then what you find here is E, and E is now again the distance between the center of gravity and the center of the shaft, but it is not the radial displacement for the equilibrium position. And what you can see is that I had to modify here for the stiffness part. I had to modify that term a little bit, and you will wonder, but where are my bearing forces and so on? The bearing forces do not appear here. What appears here is just the stiffness C of the shaft. It acts like a spring, and that spring acts with respect to the relative displacement, and the relative displacement is now the displacement related to the disk. So X now relates to the disk, and XL is now the displacement of the shaft in that cross section where we have the bearing. L refers to the German word Bearinglager here. So it's exactly the coordinate XL that is of importance for the bearing forces. They do not appear here. There's just a balance for the disk, and thus there is just the restoring force of the shaft, which is modeled as a spring. And therefore everything related to that E is with respect to the disk, with respect to this X, which is the displacement of the connection point between shaft and disk. And now we have to add a force balance at the position of the bearing, so between the bearing forces on the one hand and the restoring force here of the shaft at the other hand. So we have a force balance at the bearing between the vertical and lateral bearing forces on the one hand, and on the other hand, we balance the restoring force. So we can write this equation in dimensionless form, and the fact that we include now another stiffness here, namely the stiffness of the shaft, necessitates the introduction of an additional dimensionless parameter. What would be the form of that dimensionless parameter? Well, what we did in order to obtain dimensionless equation is first we divided everything by f. That's what you have to do here for sure also. So then you get here a value of 2, or well, you can also divide by 2, of course, by 2f here. So you would get a value of 1, but you would get something that is dimensionless. So in order to obtain something that is dimensionless, as we have here a sum of all the forces, well, if we interpret the inertial forces in the sense of D'Alembert, we would have to divide by f. And also we have to divide these balances of forces, the static balances, by f. So we would obtain C divided by f, and then we would have to introduce for x a dimensionless quantity, a dimensionless displacement, and therefore we use the Clarence. So we have the product of C times the Clarence divided by f, or 2f, which would be the dimensionless parameter that we can introduce here. And now what is done in the literature is, well, this value is taken, but the inverse is taken. Why? Well, that parameter would be a compliance. It's called gamma. because gamma equal to 0 then represents the rigid rotor. So the deviation from the model we studied before is represented by values of gamma that are larger than 1. So if that stiffness C is, let's say, infinity, so very, very large, you would have a gamma value of 0, as gamma measures the compliance. So that would be not very compliant, that rotor not very flexible. And if gamma takes on high values, then you have a very flexible rotor. That is the idea of that parameter gamma. It represents the compliance. So what will now change when we study self-excitation? Well, we already studied these two equations. These are second-order equations. They lead to a fourth-order characteristic polynomial. Now there are these force balances. These force balances do not include any higher order derivatives except for the first order derivatives. They are well hidden, but they are present. Namely, we have the stiffness and damping coefficients here on the left-hand side, but we have no inertia parts as we consider here just a quasi-static or a static force equilibrium. That means due to the first order derivatives, we add two more orders to the characteristic polynomial. So the characteristic polynomial for the Jeffcott rotor will be of order 6. Let me show this to you. This would be the dimensionless equations of motion that were obtained in the same sense as before for the rigid rotor, with one exception. There is this new term, which is now 1 divided by gamma, as we take the compliance as the dimensionless quantity and not the stiffness, therefore 1 divided by gamma. And these would be the equations of motion with external excitation here. So now let's write from this equation of motion by introduction of displacements, so of perturbations, delta x, delta y, and delta xl and delta yl, so 4 displacements. Let's write this in matrix form. Then we would have a diagonal matrix in the first two entries of the second derivative of the displacements. However, from the other two equations, we do not get any contributions. Then we would see the damping matrix in the last two rows. And the same holds for the stiffness matrix. And we would see these terms 1 divided by gamma that would couple, also appear in x bar and y bar on the one hand, and also in xl and yl. So that would couple these two displacements, delta x and delta xl, and delta y and delta yl on the other side. So this would be, again, with the right-hand side here, so with excitation by the imbalance, this would be now the system for the perturbations of the displacements. And from this you can see that the characteristic polynomial is really a sixth order polynomial. You have the second order quantities here. If you make an exponential setting, you will get lambda squared here and there, and you would get here lambda and lambda. So in the determinant you will find lambda in 6th power. Well, I will not go, you see, quite fast, I would say. I will not go too much into detail, because what we do is we repeat the steps we did before in the procedure. The procedure is the same. The focus is rather on the effect of the 1 divided by gamma. So I will not go into the technical details of every step. I think the computations are now feasible once you understood how the computations have been done for the rigid rotor. So let's study now the homogeneous equation, so self-excitation. So we need a setting for delta x bar, delta y bar, delta xl and delta yl by some integration constants or amplitudes and an exponential function of lambda bar tau. And we want to determine this lambda bar tau, or I would say we don't want to determine that lambda bar tau, but the coefficients of the characteristic polynomial in order to infer the sign of the real part of this lambda bar. Yeah, so this is here the approach for our self-excited vibrations setting. And if we insert that setting, we arrive at an algebraic system, and you can see here how that algebraic system is structured. We have the terms coming from the inertia. We have then plus 1 divided by gamma here, which comes from the stiffness of the shaft, minus 1 divided by gamma, because we have to multiply also with delta XL and delta YL, because we have to take relative displacements. You can see the same here for the shaft stiffness included in the last two terms, and from the bearing forces we get here the damping coefficients multiplied by a lambda and the stiffness coefficients, the corresponding stiffness coefficients. So from this we get our sixth order characteristic polynomial, but the only difference in that sixth order polynomial is that at some places this 1 divided by gamma appears. All the other coefficients or the other terms here in that matrix, in that coefficient matrix, are already well known and are the same. So we have the damping matrix, the stiffness matrix, and we have the omega bar squared, and they appear, I would say, more or less at the same place. Yeah? So therefore, a lot of these coefficients of the characteristic polynomials can simply be copied, and the changes due to the introduction of 1 divided by gamma will be taken special care of, I would say. Yeah? So here you can see, without going into the details, the coefficients of the characteristic polynomials. And these quantities, A0 and so on, refer to the same quantities we had before, with the simple difference that there appears now not only an omega bar squared at some places, but also a 1 divided by gamma squared. So as you can see, there are no new coefficients, but they are arranged in a different way, and they are written now such that the effect of omega bar is visible, because we want to compute a limit value for the dimensionless rotational speed. And on the other hand, we want to see the influence of the gamma parameter on that dimensionless critical speed. And therefore, also gamma has been made visible here. So this is just a strategy, very important. And I think that's what you should retain here. If there are parameters you focus on, then if you do such a stability analysis with the coefficients of the characteristic polynomial and you want to apply Hurwitz criterion, then it's a good thing to single out the influence by factors of these parameters you are interested in, and to lump together everything else. So everything else is hidden in these parameters A. Yeah? So what can be said after application of the Hurwitz criterion? Of course, the criterion is the same. We have flutter instability, but that flutter instability does not relate now to H3, but our Hurwitz matrix, as the characteristic polynomial is of order 6, is now a 6 by 6 matrix, and the corresponding Hurwitz criterion is now H5, the minor Hn minus 1. And what you get is the following result. You get the dependence of the limit rotational speed, dimensionless form of the Jeffcott rotor, L for Laval rotor, which the Jeffcott rotor is called in German, is the, well, I would say it's proportional to the limit speed for the rigid rotor, and there is a factor, and that factor is A3 tilde divided by A3 tilde plus gamma A1 tilde. What can be said in the limit case of a rigid rotor? In the limit case of the rigid rotor, gamma is equal to 0. And you can see that you reproduce, and that's good, that you reproduce the result we had before. Then for this case, where gamma tends to 0, the result tends to the rotational speed of the rigid rotor. Now, what can be said if gamma is not 0? And keep in mind that gamma is positive. Well, if you look at that expression, then you find that A3 plus gamma A sub 1 is always larger than A3. Keep in mind that A sub 1 is always positive. We discussed this. No, we did not discuss, but you can can look at it. So A1 is always positive. So this quantity is always less than 1, the factor. That is the additional stiffness, I would say the additional flexibility included in the system reduces the limit value. I could say the critical speed, but in a sense, not in the sense of a resonance, in the sense of that instability. It reduces the limit value for the rotational speed. And this makes sense. You add a flexibility to the system and that critical speed is reduced, goes down. No? So we find here a result that, well, perfectly matches our expectations. So the conclusion are, due to the compliance of the shaft, there is a reduction of the rotational velocity at the stability limit. So you reach the stability limit earlier when taking the compliance of the shaft into account. So when taking these flexibility effects into account. And there is another result I'm not going to show here, but if you look at the natural frequency for these undamped oscillations at the stability limit, you will find that the frequency ratio is nearly unchanged by this additional flexibility. So it applies to the stability limit, but it has nearly no effect on the frequency ratio. Well, that's already all I would like to tell you. See, I'm going on rather fast compared to the other videos now. I would like to tell you about the self-excited oscillation. For the imbalance excited oscillations, we just look again at the particular solution. We generalize the ansatz we had before. So we take the cosine tau, we take the sine of tau, and we take amplitudes xc, yc, and xs, yss before. But we have to add additional, well, I have to say the original amplitudes are those here we had before, because they refer to the bearing situation. These are the amplitudes we now consider for the disk. No? So, but we have to enlarge the vector of amplitudes from 2 dimensions to 4 dimensions. Then it's possible, of course, to insert that ansatz, that setting, into the equation of motion, now the inhomogeneous equations of motion, and to obtain an algebraic system that is now 8-dimensional, because we have to determine 8 parameters, 8 amplitudes here. And from this we can then infer on G, which is the most important parameter for us. So the radius of the longest direction of that ellipse that is obtained. And this is now a function, as before, of omega bar, Sm, and epsilon. Again, epsilon here refers to the imbalance, and of the additional parameter, and that's of interest for us, that gamma. Well, in order to represent the influence of gamma on G, and to represent G, I introduce a new parameter here, which is omega bar times square root of gamma. Well, for omega bar, we had Cm divided by F times omega, when we take the square root of Cmf divided by F. For gamma, that compliance, we had 2F divided by C and C, so stiffness and clearance. And as we take the square root, there is the square root here. So if you do the computations, then you will end up, well, you see that the F goes away, and the same holds for the clearance, and you get a ratio of 2m divided by C. Now keep in mind that we always called the mass of the rotor, I know that's a little bit strange, we called it 2m. 2m is the mass of the rotor because we wanted to divide the whole equation by 2. So as 2m is the mass of the rotor, 2m divided by C square root is just what we would call for a Jeffcott rotor the critical speed, the natural frequency of that vibration system composed by a disk and a flexible shaft. So therefore we have here the ratio of omega divided by omega k, so it's still square root 2m divided by c, and for square root 2m divided by c, we have 1 divided by omega k, which is what we call the critical speed for a Jeffcott rotor, and what would be the natural frequency of that Jeffcott rotor. So we have the ratio. If we consider that quantity, we have a kind of frequency ratio between the rotational speed of the rotor and that critical speed. We would expect things to become difficult, so G values to become very, very large if that ratio, if that quantity is larger than 1. So then let's plot G over that value omega bar square root of gamma. Well, not G, but a dimension is G, namely G divided by or related to this epsilon here. Yeah? And we fix now one value for sigma, and also sigma now can relate it to square root of gamma. So we fix this parameter and we vary gamma. Keep in mind, gamma equal to 0 is a rather rigid rotor. Gamma very, very large, you can see this here, is a rather flexible, so rather soft rotor. So what can be seen where you would expect if there is a resonance, then it should occur at values of square root gamma times omega close to 1. And you see that this is the case for the flexible rotor. For the very rigid rotor, you see that this resonance does not play a large role, and that you shift the high amplitudes, well, not so high, but higher amplitudes, of course, to the low frequency regime. I would call it, better to call it the low rotational speed regime, so the subcritical regime. So what can be concluded here, if we have a large compliance here, very soft rotor, then we have large maxima, and these occur close to resonance. So the critical rotational speed has nothing to do, we are here at external excitation, with the self-excited limit speed studied before. So the critical rotational speed here for that rotor would be close to the natural frequency of the Jeffcott rotor. Classical result. However, in the case of a small compliance, so a rather rigid rotor, or resonance, if we call that resonance, I would say the peak appears at very low rotational speeds. Sometimes there are two local maxima possible. So you can see there's one here and another one there. But you can see that they are not very pronounced. So that would be a kind of resonance. So a kind of thing one has to pay attention, but it is not, of course, as dangerous as these large amplitudes here. And for very, very stiff rotors, one can see that the first, it's a little bit difficult to see here for these values because there seems to be a slight peak, but you can see that the first, for the two cases, that the first local maximum is also the global maximum. So it appears here already at the first maximum, and you can see that either you are below that first maximum, well, that would be rather static, or you are supercritical already if you pass that first maximum here for rather stiff, close to rigid rotors. And therefore you can see that taking the flexibility into account is very important for soft rotors, where you have that very pronounced resonance, but for rather rigid rotors, this is not necessary. Well, that's already everything in a very quick way. I would like to tell you for the Jeffcott rotor in journal bearings. And with this, I would like to close not only one chapter, I would say two chapters, and a very large part of that course on machine dynamics, namely related to journal bearings. First, the model for the journal bearings and the computation of the bearing forces and their linearization. And second, to study the influence of these journal bearings on the stabilities of rotors, namely rigid and flexible rotors in the sense of the Jeffcott rotor. So enough on rotor dynamics. The rest of the next chapter of that course in machine dynamics will be devoted to belt drives, and therefore to continuum vibrations. So we will see, so the rest of the machine dynamics 2 course will be in fact related to continuum vibrations. We will now see continuum elements like these belts or like blades of turbines that vibrate, and we would like to study in more detail and understand a little bit better these vibrations, these continuum vibrations, and therefore we have to study partial differential equations and how to get information in the sense of vibrations, natural frequencies, amplitudes, and so on, for or out of partial differential equations. So in the next video, I will start with the belt drive. Thank you very much for watching, and I hope to meet you again in the video on belt drives.